Section 5.2, the indefinite integral. All right, up till now we've been taking derivatives, taking derivatives, taking derivatives, taking derivatives. Well, what we're about to start doing for 5.2 and beyond is we're going to go backwards, okay? We're going to start with the derivative, and we're going to find the function that it came from, okay? That's what we call anti-differentiation or integration is what we call it, okay? All right, let's look at this function. Capital F of x is equal to 7x to the fifth minus 2x squared. If you were to take the derivative of this, and you were to call that derivative lowercase f of x, let me get a different color here. Let's suppose we would take the derivative of this and we would call it lowercase f of x. Instead of f prime, I'm just going to call it lowercase f of x. What would that be? 35 x to the fourth minus 4x. So what we can say here is that this function capital X, or capital F, I'm sorry, is an antiderivative of lowercase f. In other words, what happens a lot of time in real life is we notice the derivative. We observe the derivative, but we need to get back to the regular function. So we start out with the derivative function, and we take an antiderivative to get back to the original function. All right, let's see. I already did this one for some odd reason. I don't know why, but let's say we were to take the derivative of this capital F of x and call it lowercase f of x, okay? What's the derivative of e to the 2x? E to the 2x times the derivative of the exponent, so times 2, right? So what we could say there is that uppercase f of x is an antiderivative of lowercase f. Or I could say e to the 2x is an antiderivative of 2 times e to the 2x. How about this function? Let's take the derivative of this function and call that lowercase f of x. What would that be? 3x squared plus 0? So we could say that capital F is an antiderivative of lowercase f here. How about this function? What if I take the derivative of this one? I get what? 3x squared, right? So I could say x cubed is an antiderivative of 3x squared. But wait a minute, we said that x cubed plus 2 is an antiderivative of 3x squared, because that's the same thing, right? Actually, both of these are antiderivatives of 3x squared. In fact, you see how we're calling it the indefinite integral? That's why, because we don't get a definite answer whenever we take the antiderivative here. We're getting what? Answers that differ by a constant. This one has plus 2, that one has plus 0. What if I had capital F of x is equal to x cubed plus 7? And I took its derivative. What would that be? 3x squared again? So I could say x cubed plus 7 is an antiderivative of 3x squared. But notice the 3x squares. All their antiderivatives are x cubed, but they differ by a constant that's added to the end of it. So whenever you're finding these antiderivatives, basically, what you're doing is this. You're finding a whole family of functions is what we call it. Let's see. So this antiderivative is x cubed plus 2. This antiderivative is x cubed. This antiderivative is x cubed plus 7. What if I graph those antiderivatives? X cubed. What does that look like? Looks like that, right? What if I graph this antiderivative? X cubed plus 2. Well, that's the same graph. It shifted what? Up 2 units, right? And what if I graph this antiderivative? That's the same graph. It shifted up what? 7 units. Okay? But the important thing is they all differ by a constant, okay? All right, so let's look at what we call integration, antiderivative or integration, okay? What if I were to tell you, okay, y'all agree with this? If capital F of x is equal to e to the 2x, its derivative is 2e to the 2x. And we said that capital F of x is an antiderivative of 2e to the 2x. So the way I write this is like this. Do an elongated s, and I say, okay, 2e to the 2x. And I put a dx there because that tells me what variable I'm integrating with respect to, okay? So I'm starting out with the derivative here. And what this basically means is find an antiderivative, okay? So don't already know that an antiderivative of that is d to the 2x? I sure do. But I'm going to put plus a c here, plus some constant, okay? I don't know what that constant is. It could be 3, could be 7, could be 5, whatever. So I just put plus c. What about if I were to do this? What if I were to start out with the derivative function, 3x squared dx, and I put this notation? That would mean find an antiderivative of 3x squared. So it's what? Antiderivative of 3x squared, we said was x cubed plus 2, or just x cubed, or x cubed plus 7. But either way, the antiderivative is going to be x cubed plus some constant, right? The constant might be 2, the constant might be 7, the constant might be 0 over here, okay? So what does this notation mean again? Integrate or find an antiderivative, okay? In fact, your book talks about the process of finding antiderivatives is called antidifferentiation or integration. And they write it this way. They write, let's suppose that we have the integral of f of x dx like this. They call it capital F of x plus c. And then they say, okay, here's your derivative function. There's your antiderivative function, okay? Now, let's go over some terminology real quick whenever we use this integration symbol, okay? So if I have something like this, the integral of f of x dx, we call this elongated s the integration sign or integration symbol. This f of x, whatever it ends up being, like x cubed or 5x minus 7 or whatever that we're taking the integral of, we call the integrand. All right. Then we have this part, and let's add one thing to this part. Let's put where c is an arbitrary constant. Let me just check my spelling of arbitrary. Arbitrary, I think I spelled it wrong. B-R-T-U. There we go. How about that? All right. Let's look at some integration, okay? In fact, I'll tell you what, let's look at this power rule, okay? The book talks about to integrate a power of x other than -1, add 1 to the exponent, and divide by the new exponent. So for example, let's suppose I want to integrate x to the 7th with respect to x, okay? I'm integrating a power of x other than -1. So what do I do with that power? Add 1 to it, 7 plus 1 is 8, and divide by that new exponent, and put my plus c. Now, double check yourself. Make sure that's right. What if you take the derivative of this? If you take the derivative of this, you should get the inside. You should get this integrand back. Do you? Well, 8 times this 1/8 will be 1. X to the 7th plus 0. Yeah, I get x to the 7th, okay? How about this one, part B? What about the integral of x to the -5 dx? Now, is this a power of x other than -1? Yes. So what am I going to do? My book tells me add 1 to this number. So I'll give me -4, divide by the new exponent of -4, and put your plus c, your arbitrary constant. Now I could clean this up. I could call this -1/4x to the 4th plus c. take a look at C, part C. We're going to have the integral of the cube root of x squared dx. All right, first thing, let's write this as an exponent. So this will be the same thing as the integral of x to the 2/3 dx. Now, is that a power of x other than -1? Yes, it is. So what do? Add 1 to this number. If I add 1 to that number, I get what? 5/3? Divide by the new exponent of 5/3 and add your arbitrary constant. Well, we definitely don't want to leave it this way. We want to multiply by the reciprocal here. So we're going to say 3/5 times x to the 5/3 plus c is an antiderivative of this function, okay? Let's look at properties of indefinite integrals. Properties of indefinite integrals. Properties of indefinite integrals. All right, your book has this, and your notes also have it. The integral of c times f of x dx is equal to c times the integral of f of x dx. So what does that mean? That means if I'm trying to integrate a function that has a constant multiplied here, I could pull the constant to the outside of the integration symbol. We also have a property that says this. Suppose I have f of x plus g of x, I'm trying to integrate. Well, if I have two functions being added in my integrand, I can break those up as the integral of the first function plus the integral of the second function plus the integral of the second function plus the integral of g of x. And we also have a property for subtraction that basically says the same thing. Suppose I have f of x minus g of x. I'm trying to integrate. I could break that up into the integral of the first one minus the integral of the second one. The integral of the first one minus the integral of the second function. Now notice, you can pull the constant outside the integral sign if it's multiplied. If you have two functions added, you can integrate each one and add that. If you have two functions subtracted, you can integrate each one and subtract it. But there is no property for f of x times g of x, okay? It does not work that simple. In fact, in general, that's a much more complicated problem. All right, so let's use these properties. In our notes, what do we have? We have an example, then we have part A, and it wants us to integrate 4x squared plus 2x cubed minus 5x dx. All right, look at what I have. I'm integrating stuff that's being added and subtracted, right? So those properties, those last two properties just told me I could break this up into separate integrals. I could write this as the integral of 4x squared dx plus the integral of this part, plus the integral of 2x cubed dx, minus the integral of this part, minus the integral of 5x dx. Comme ça. All right, we also had a property that told us this. It told us if we have a constant multiplied by my function, I could pull that constant to the front of the integration symbol and write this as 4 times the integral of x squared dx. Plus a constant multiplied by my function, pull the constant to the front, 2 times the integral of x cubed dx, minus, same thing here, 5 times the integral of x dx. So we have 4. Now, how do I integrate x squared? That's a power of x other than -1. So what do I do with it? Add 1 to that, divide by the new exponent, right? Plus my arbitrary constant c. That's the integral of this part. Technically, I guess I need this, really. All right, plus, bring down your 2. Now take the integral of this part. That's x to the fourth over 4 plus c, right? Minus 5 times, let's take an antiderivative here. What is that understood to be? 1. So it'll be x squared over 2 plus c. Now we have a bunch of plus c's here. And this c isn't necessarily the same as that c, and they're not necessarily the same as that c. So I'm going to call this one maybe c subscript of 1, c subscript of 2, and c sub 3. Because they might be 3 completely different numbers. Alright, well let's rewrite this by distributing 4. So I have 4/3 x cubed plus 4 times c1. Plus, if I multiply 2 by this, I get 1/2 x to the fourth plus 2c2. Then if I distribute -5, I get -5/2 x squared minus 5 times c3, right? All right, let me ask you this. What's 4 times c1? Just some constant, right? What's 2 times c2? Some new constant. What's -5 times c3? Some new constant, right? What's a new constant plus a new constant plus a new constant? A new constant, right? So instead of writing this part, and this part, I could just write that all as one c value, okay? That's some new constant, just c, I could say. So what I'm going to do is bring down 4/3 x cubed plus 1/2 x to the fourth minus 5/2 x squared. And instead of all this stuff that's underlined in blue, instead of calling it 4c1 plus 2c2, I'm going to call it plus c. There we go. There is an antiderivative of this function right here. Now, what we're going to start doing though is whenever we have like things added and subtracted, functions added, subtracted here, we're going to skip all this breaking it up and so forth because it just takes too long. I just wanted to show you how you use those properties. But really, I could have done this way instead. I could have said, okay, let me take the antiderivative of this part. Okay, so I have 4 times, what's the antiderivative of x squared? X cubed over 3. Plus, take the antiderivative of this part, 2 times x to the fourth over 4, minus 5 times the antiderivative of this part is x squared over 2. And technically I need c1, c2, c3, but I know they're all going to add up to some new constant anyway, so I could just put plus c at the end there. And if I clean this up, I get 4/3 x cubed plus 1/2 x to the fourth minus 5/2 x squared plus c. And is that the same thing I got earlier? Sure it is, right? That's a much quicker way to do it. Let's look at part B. Let's look at part B. Part B. All right, so for part B, we have this. We have, let's integrate y plus the cube root of y in parentheses times, open a new set, 4 minus y squared, close parentheses, dy. Now, what's the difference here? We have y, so we're integrating with respect to y. But it's really the same thing if we put x here, 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 and here, right? It's just some variables, what they're saying. All right, so let's take an antiderivative. Let's find an antiderivative. Well, remember those properties I had? They worked for what? Addition and subtraction, but they did not work for when your integrand was being multiplied here. So I definitely cannot take the antiderivative of this one and multiply by the antiderivative of that one. If you do that, you will go straight to hell. Well, probably not, but you can't do it. It's mathematically wrong. All right, so what do we do then? We're stuck? We just go home, we quit, give up? No. What do? Well, what we do is we just multiply this stuff out first before we take an antiderivative, okay? So what I'm going to do, bring down my integral sign, and I'm going to use the distributive property and say y times 4 is 4y, y times negative y squared is negative y cubed. Well, this is really y to the 1/3, right? What's y to the 1/3 times 4? 4y to the 1/3. And what's y to the 1/3 times negative y squared? Well, what do? You take that 1/3 and add it to the exponent of 2. So that's what? 2 and 1/3, right? What's 2 and 1/3? 7/3. I'll put all that in parentheses and bring down my dy. Now look at your integrand. It's just functions being added and subtracted, right? So I can use those properties and take the integral of this part, that part, that part, and that part, and add and subtract them. So if I take the antiderivative here, the 4 is out front times, what's the antiderivative of y to the first with respect to y? Y squared over 2. Minus, what's the antiderivative of y cubed? Y to the 4th over 4. Plus, bring down your 4 here. What's the antiderivative of y to the 1/3? Well, add 1 to 1/3. What does that give you? 4/3 divided by 4/3. Minus, how about the antiderivative of y to the 7/3? Add 1 to 7/3. What does that give you? 10/3 over 10/3. And what do we need to put at the end? Plus that big old fat c, right? All right, let's play clean up here. This will give me 2y squared minus 1/4 y to the 4th. Now, what I can do here is I can multiply by the reciprocal to simplify this. And if I multiply by the reciprocal there, I get what? Plus 3y to the 4/3. How about this part? What if I multiply by the reciprocal? I get minus 3/10 y to the 10/3 plus c. And there's an antiderivative right there. See how we're doing on time right here. Oh, 22 minutes already.